All right, well, I think that's everybody. So, I guess what we can do is we can just move on. The next thing we're going to look at is piping and instrumentation drawings. Basically, this is exactly the same as electrical drawings, but it's for plumbing. Right. What we have is, it's a set of symbols and diagrams that's used to illustrate things like the hardware, the types of signals, the connections, and the instruments. In Australia, we're supposed to use AS 1101.6. Slight problem with that is that AS 1101.6 had been withdrawn some years ago, and we don't actually have an AS anymore. So there's many unofficial alternatives, and frankly, most of them are a lot better than AS 1101.6, which was a heap of crap. So, when you get a set of P&ID drawings, as they're called, then generally you'll find a few pages on the front of this drawing, a set of drawings, and they're like the glossary. That's the index, and that's the symbols that the person who did the drawing has used. The first thing is that we name all the instruments and we label all the instruments. All the instruments, all the instrumentation stuff is labeled using what's called a tag name. This tag name is used throughout the entire factory, and it's used in the maintenance records, in the fault finding, in the identification, in the databases for PLCs and SCADAs. There are rules for tag naming. There's an ANSI rule system and a German system, but there isn't a set of rules for mine sites. The tag name should reflect the process variable, that's the thing that you're measuring or controlling, and the function. This table is what we're supposed to use for generating tag names. And what you're supposed to do is you're supposed to use the first column to give you the first letter, either this or this column, and that gives you the first letter, and then any other letters you get from these columns. So that, for instance, if you had a flow valve, that would be from the first column, we look up flow is F, and from the second column, from the succeeding columns, we find valve, and we find valve over here, and that gives us an FV. So FV is flow valve. There are some slight differences in that D for the first letter can mean density, or it can mean differential. Q can mean quantity, or it can mean integrate. S can mean speed or safety. So it's a little bit of a messy system. What I've done is, when you get your books, you'll find I've made a glossary of the most common used values, so you can just look them up in alphabetical order. That's the easiest thing. When we talk about loops, when we talk about instruments, we use a set of digits, FV for flow valve, and then we number them so that we know which flow valve is which. So we've got flow valve 102, and if that is connected to a tank, that would probably be tank 102, and if there was a pump, it would be pump 102, so that all of them are connected together, and they're all together. They're all part of loop 102. We place tags inside what we call balloons. A balloon. It's called a balloon because it can get bigger. So that if you have a big tag, FICR, rather than trying to fit it inside a nice little circle, you can let your balloon get bigger. so that it can inflate, you see, and everything can fit in nicely. So FICR would be a flow indicator controller recorder. We put the ID, the letters, on the top, and we put the numbers underneath. Different lines mean different things. So this would mean control room mounted, or control room. A square around it means it's got a shared display. Once again, in your books, when you get your books, there's a whole glossary that explains what all these different things mean. Now, moving right along, and yes, Ron, I have turned on the recorder. One special bunch of symbols is what's called the alarm symbols. And there are 4 special alarm symbols: high and low, high high, and low low. Now these are different. What high and low means the gauge is all right, but it's just out of spec. So the stuff we're making is just out of spec, but the instrument is reading just fine. High high and low low, they mean the instrument's broken. Don't take any notice of it. So that if you had a room temperature sensor, for instance, then you could maybe have a high as 30 degrees C and a low of 10 degrees C, because that would make you uncomfortable. But you would have a high high of 100 degrees C and a low low of 0 degrees C. I'm talking about in Australia here. And because you'd pretty well figure that if you had a room temperature sensor that was reading 100 degrees C or was reading 0 degrees C, and we're in Australia, so we're in Perth, Australia, then those gauges must be broken, because it's unlikely to be the boiling point of water or the freezing point of water inside a room. At least you'd hope not. So in that case, rather than act on what the gauge is giving you, ignore it. Ignore the gauge readings, go to the secondary gauge, or shut down the control system, because that high high or low low indicates that the gauge is out of spec, the gauge is, sorry, not out of the gauge is broken, and the values it's giving should not be acted upon. Okay. Another set of standards we have is pipeline codes. And different colours, we're supposed to have, all the pipes in our plant is supposed to be painted different colours. And those different colours mean special things. So that green means water. That's not drinking water, that's just water, wastewater, general water, stream water. Silver is steam. Generally speaking, that means it's hot. Steam being quite a hot thing. Brown, oils. Yellow is gases. Violet is acids or alkalines. Things that if they got on you will burn. Light blue is air. Black is other things, undefined really. Now one that is quite annoying is orange. Electricity should be in orange pipes, it should be in orange conduits. Now the reason that's annoying is because our standard indoor type conduit is grey. So what will sometimes happen is you'll install a whole load of beautiful new grey conduit and someone will come along and paint it orange. Safety red is firefighting, and that should never be changed colour. Safety yellow with black stripes means dangerous. Safety yellow with a black trefoil, and I'll just draw a trefoil. Trefoil looks like that. So that's the radiation symbol. So that means ionizing radiation. And finally, blue, or auxiliary blue, that means drinking water. Now here we have a typical P&ID drawing. And what we have is we have different, this is piping coming in. Here we have a flow indicator, a flow tube, something that's measuring flow. We're going through this. We've got something here, I'm not sure what it is, and we go into this object here. And then the fluid goes this way. And we have, it seems that we have steam coming in here and going out here. So that's the piping part of the P&ID. The instruments are all stuck out in balloons. So each one of these instruments is each one of these balloons represents an instrument. Okay, now I'm going to ask some questions, either type in or put your hand up, but does anybody know what this thing is? This thing. Yep, I think several of you got it. It's a valve. Now, it says here TV. T for, what would T stand for? Yes, indeedy, temperature valve. So this valve here, this valve controls the temperature. And what we have here is it's called TV101. We have over here TRC, Temperature Recorder and Controller 101. So we're measuring temperature here. The controller is outputting to the valve. And that controls, well, that valve must control the flow through this heat exchanger. And so by reducing the flow, the temperature of the fluid coming out would increase. Now we have another valve here. Now what do you suppose FO stands for? What about open, Matt? Nearly. It's actually failure. FO, fail open. It's what the valve does in the event of a fire, in the event of a disaster, in the event of a breakdown. If the little nylon pipe that's carrying the air, see this, where's my pointer? This thing here, this is a nylon air pipe. In the event of a fire, that will melt. This here is a nylon air pipe, and that will melt. In the event of a fire, I want this valve to fail open. I want this valve to fail close. Now that's fair enough if you look at it. This is steam. In the event of a fire, I want to shut the steam off. In the event of a fire, I want to open the water up, because this heat exchanger would have got very, very hot. So opening the water up would cool the heat exchanger down, because the last thing I want is for this heat exchanger to crack open. In general, the rule we have with fail open and fail close is that we do two steps. The first step is remove the source of heat, and the second thing we do is remove the heat. So the first thing we would do is remove the source of the heat, and in this case the source of the heat is the steam. So we shut the steam valve off, and then we remove the heat, and we do that by opening up the water valve. We either open the water valve, or we either fully open it or partially open it, but we make sure that there's water flow. So we have a fail close valve here and a fail open valve there. Oh, there's a quick test here. Can't really do that because the answers are being written in.